Hello everyone, this is Sanjeev Ganji starting our group's video presentation. In this video, we'll be talking about the Monte Carlo tree search, which is a search algorithm used extensively in most modern artificial intelligence programs. Unlike hard-coded functions, it helps the AI think for itself. This helps it function in a very open-ended environment such as chess, where the number of states and choices are astronomically high. Monte Carlo search is a probabilistic and heuristic driven algorithm that combines the classic tree search mechanics with modern machine learning capabilities. Notable application of the tree search was seen when Google's AlphaZero Chess AI won the 2016 World Chess Championship, defeating the likes of Stockfish and Deep Blue chess engines. The algorithm of Monte Carlo tree search is useful as it helps the program to exploit strategies that are already found to be the best, but also exploring alternative decisions. This ensures that the AI is not overlooking any potentially better paths, blinded by the provided best solution in front of it. This exploitation trade-off helps to provide the optimal solution in the provided time. To begin with, let us compare it with its predecessor, the Minimax search. Monte Carlo search was introduced in 2006 at a time when most chess AI were using the Minimax tree search. Minimax search compared to Monte Carlo is primitive and has high processing time. Minimax is limited by how deep it can see into the game tree, and it is inefficient at exploring and solving complex positions. The new algorithm brought revolutionary changes with it. For starters, although both were game tree searches at their core, Minimax search needed a defined heuristic search to evaluate its states, while Monte Carlo uses all of its provided time to run random iterations exhibiting a simple anytime behavior. Monte Carlo search, unlike Minimax tree search, uses a strong evaluation function at its core to search for optimal solutions from random playouts in the game state. However, Monte Carlo search comes with its fair shares of negative aspects. For starters, it is observed that Monte Carlo search does not detect shallow traps where the opponent can win in a few moves. In such cases, Minimax search with alpha-beta pruning still remains superior. Monte Carlo search performs poorly when it is not allowed to run enough iterations. This makes the selected moves seem like random legal moves picked by a toddler. Monte Carlo search always evaluates alternative strategies periodically to explore and improve the current optimal strategy. We will now talk deeply about the algorithm involved in Monte Carlo tree search.
Now that we know how traditional board game AIs used to work and their limitations, it's time to explore Monte Carlo tree search, a very efficient algorithm that is way ahead of Minimax search algorithm. My name is Aryan Satpathy, and I'll be explaining Monte Carlo tree search. So the key differences between Monte Carlo tree search and Minimax are: number one, it only searches a set of interesting moves, so as to speak, rather than all the possibilities, like Minimax does. Search space is greatly reduced by doing so, and we still manage to get accurate predictions. Number two, we perform simulations or rollouts, which basically means play random legal moves so as to reach a terminal state, i.e., game is over. And we keep track of the number of victories, draws, and losses, starting at each node. Number three, the interesting moves that I talked about earlier, they are determined by the ratio of number of wins to the number of simulations. Well, it is slightly different from this, but we'll discuss it after a while. Number 4. The number of simulations or rollouts can be fixed so as to take into account time limit for computation. Now we shall go on and understand the algorithm. We start with our start node, which is current position on the board. In Monte Carlo tree search, we have 4 basic steps, which are repeated in a loop. We start off with expansion. Now in expansion, we expand a node by making a child node for each possible legal move from the current state. As you can see, we assign them all 0 wins in 0 simulations. Next off, we do simulation, which basically means that we play random moves from the current node so as to reach terminal state. This can be either a win, or a draw, or a loss. Now that we have simulated, we backpropagate to parent nodes and update the win and number of simulation values. This step is called updating. We must repeat the process of simulation and updating for each child node that we just expanded. Once it is done, we go back to the start node and do our next step, that is selection. In this, we simply select the most interesting child at each point till we reach a leaf node, and we expand the leaf node as discussed before, and so on. This procedure is repeated in a loop. Now at the end, the predicted move is a child with the highest number of simulations, not the highest number of wins. Now how exactly do we select the most interesting child? We select the most interesting node not on the basis of win to simulation ratio, but as per this value. It is the ratio of win to simulations plus square root 2 times logarithm of total number of simulations divided by number of simulations at the current node. Now we shall take a look at the improvements done over basic Monte Carlo tree search. When we think about Monte Carlo tree search, the biggest success is DeepMind's AlphaGo. It beat Lee's doll, who was winner of 18 world titles on March 2016. The AI won the game by 4-1. So how does AlphaGo work? They implemented deep learning to Monte Carlo tree search. The selection step was done by a policy network, which is a neural network. Instead of continuing simulations all the way till the end, they were evaluated by value network, which was once again a neural network. The policy network was trained by a human dataset, and the value network was trained in the same procedure that is followed in reinforcement learning called value iteration. Now AlphaGo is very strong, but it still had some room for improvement. The obvious issues were its dependency on human dataset to train the policy network. Apart from that, we were also facing overfitting issues as we were only changing the value network. Then DeepMind developed AlphaZero. This combined the policy and value networks so that while training, the overfitting issue is addressed. Training didn't require human dataset anymore. Rollout step was entirely removed and value network was used to estimate the possibilities lying ahead. Let's take a look at how it is trained. It is trained completely by self-play. The networks are allowed to play the game, and at the end of the game, the winner is noted down. And the network is updated according to the result. Now the AI is better than its previous self. We keep repeating the process and the AI gets progressively better and better. So that will be the end of my explanation to Monte Carlo tree search.
We have discussed what Monte Carlo tree search is. Now, let's talk abstractly about some things that actually makes it so powerful. Monte Carlo tree search is a family of directed search algorithms that has become very popular lately. Despite of having invested a vast amount of research into Monte Carlo tree search, the true nature of the effect of modifications on the algorithm as well as the manner in which it performs in various fields is still a challenge to be fully known. In particular, the selection procedure in the Monte Carlo tree search is somewhat tricky. The difficult choice between the selection of a less explored node over the more informed one induces the majority of problems. But at the same time, if handled carefully, this meticulous selection of different nodes leads to amazing results. Rollouts, as defined by Monte Carlo, are the phase in which random actions are taken. It is basically the decision process where we need to look what state transition path we need to take in order to get in the most probable solution to the problem. This is the make or break step in the Monte Carlo tree search algorithm. It is found that knowledge-heavy rollouts often result in worse performing agents. Therefore, the effect of using knowledge heavy rollouts is often confusing. Under certain smoothness conditions, it is found that uniformly random simulation policies preserve the ordering over action preferences. This explains the Monte Carlo tree search or MCTS success. Despite using sampling procedures instead of well-informed heuristic function, it is able to generate next to ideal versions of AI bot engines in the most complicated games like Go and chess. The method has become a state-of-the-art technique for combinatorial games. However, in more complex games like those with high branching factor or real-time ones, and as well as in various practical domains like transportation, scheduling, or security, an efficient MCTS application often requires its problem-dependent modification or integration with other techniques. But it is also found that completely neglecting ordering or information that is going completely random leads to disappointing results as well. So the take here is that we need to find a sweet spot between informed and random ordering such that we look towards the beneficial as well as less explored nodes in a balanced way to find the best action possible. In summary, the main advantages of MCTS which differentiate this method from the majority of other search algorithms can be summarized as follows. First of all, the problem tree is built asymmetrically, with the main focus on the most promising lines of action and exploring options that most likely may become promising. Second of all, it is the most popular way of assuring the exploration versus exploitation balance in a theoretically provable way. Furthermore, the method is inherently easy to parallelize. And finally, MCTS is the so-called anytime algorithm. That is, it can be stopped at any moment and still return reasonably good solution. That is, the best one found so far. On the downside, since MCTS is a tree search algorithm, it shares some weaknesses with other space search algorithms. For instance, is prone to search space explosion. MCTS modifications such as model simplifications or reducing the action space are one way to tackle this problem. A different idea is to use MCTS as an offline teacher that can be executed for sufficiently long time and generated high quality training data. Then another method that is not search based but rather learning based and inherently capable of generalizing knowledge. The example, an ML model, is trained on these MCTS generated training samples. Consequently, a computationally heavy process is run just once, and then this time efficient problem representation can be used in subsequent online applications. The approach of combining an MCTS trainer with a fast learning based representation can be hybridized in various ways, specific to a particular problem or domain of interest. In the end, we would like to stress the fact that MCTS, originally created for Go, was for a long time devoted to combinatorial games and only recently started to expand its usage beyond this domain. Lastly, we would like to thank all our professors and teaching assistants for helping us throughout this journey of exploring the world of Monte Carlo tree search.